Welcome students, welcome to my new lecture. Today we are going to start the first lecture of Advanced Engineering Materials, and I am Muhammad Tanbir Ahmed, lecturer, Department of Civil Engineering, World University of Bangladesh. Today we are going to discuss about the most important properties of engineering materials such as stress, strain, modulus of elasticity, toughness, ductility, etc. And we also discuss about the typical stress strain curve of mild steel. Properties of engineering materials. A quality that defines the specific characteristics of a material is termed as property. The properties of material provide a basis for predicting its behavior under various conditions. They are the tools the engineer uses to solve his materials problem. Some of the most important properties of engineering materials are: first, on physical properties. Shape, size, density, porosity, structure, etc. belongs to physical properties. Mechanical properties. Strength, elasticity, plasticity, stiffness, etc. belongs to mechanical properties. Then chemical properties. Corrosion resistance, acidity, alkalinity, etc. are the chemical properties. Thermal properties. Specific heat, thermal expansion, conductivity, etc. are thermal properties. Magnetic properties. Permeability, cohesive forces, etc. belongs to these properties. Electrical properties, conductivity, dielectric permeability, etc. belongs to electrical properties. In civil engineering perspective, these physical properties and mechanical properties are most important. Now we will discuss about most important properties of engineering materials. First, we will discuss about the strength. It is the property of material that permits its ability to resist internal forces or stresses. In another way, we can say it is the property of a material which opposes the deformation or breakdown of material in presence of external forces or load. Now, stress. Intensity of force or force per unit area is called stress. Stress is the intensity of internal force developed when an external force is applied on an engineering materials. It is denoted by sigma, and we can write as sigma equal to P by A, where P is the applied force or pressure and A is the cross-sectional area of the object or body. Stress is again three types. They are tensile stress, compressive stress, and shear stress. First, we will discuss about tensile stress. This type of stress is induced in an engineering materials when it is subjected to tensile force. And simply we can write as tensile stress is the ratio between tensile force to that of the area under tension. Compressive stress. This type of stress is induced in an engineering materials when it is subjected to a compressive force. And as like as tensile stress, we can write that compressive stress equal to compressive force divided by area under compression. Shear stress. When a part of engineering material tends to slide over another portion at a given section, the fibers at that sections are said to be shear, and this is called shearing stress. Normal stress. The stress acting perpendicular to the curved surface is referred to as normal stress. A normal stress is a stress that occurs when a member is loaded by an axial force. The value of the normal force for any prismatic section is simply the force divided by the cross-sectional area. Average normal stress sigma equal to P by A, where A refers to the average area at that section which is perpendicular to the force P. Strain. When load is applied to a material, not only stress is induced in the fibers, but the size or shape of the material is also changed. Strains are the geometrical deformation of a material due to application of an external force. In other words, strain is a measure of the deformation produced by the application of external force. Simply, the ratio of the change in shape to the original length is called strain. The change in length or deformation is denoted by delta, and we can write strain epsilon equal to delta by L. And here delta is the deformation in length and L is the original length. Here is an example. Let's read the question and try to solve this. A bar with a circular cross section is subjected to an axial tensile force of 100 kN. So this is the bar which is circular in cross section and its diameter is 25 mm, and it is subjected to a tensile force which is 100 kN. The measure of elongation is del equal to 1.5 mm. That means this bar has increased in length in 1.5 mm due to this tensile force of 100 kN. Calculate the tensile stress and strain in the bar. We know tensile stress sigma equal to P by A, and where P is the applied load which is 100 kN, and this 1000 has multiplied here to convert it in Newton, and this A is the cross-sectional area of the bar, and as this is the circular bar, so we can write A equal to pi d square by 4. Here d is the diameter which is 25 mm, and finally we get 204 megapascal as tensile stress. Again we know strain epsilon equal to del by L, where del is the change in length or elongation which is 1.5 mm, and L is the original length. The original length is given as 3.5 meter, and this 1000 has multiplied here to convert this meter into millimeter, and finally we get strain equal to 4.3 into 10 to the power minus 4. Here is another example. Let's read the question and try to solve this. If the allowable stress at failure for the material is 35,000 psi and the applied load on the bar is P equal to 20,000 pound, what is the minimum area required to prevent failure? In this question, allowable stress sigma and load P is given. We need to calculate area, that means A. So we should go the equation of stress, which is stress sigma equal to P by A. From this equation we can write A equal to P by sigma. Here P is the applied load which is 20,000 pound, and sigma is the allowable stress which is 35,000 psi, and finally we get required area A equal to 0.57 inches square. Strength. The maximum stress that can be withstood without failure is called strength. As like as stress, the strength are of the following types. Compressive strength. The maximum compressive stress a material can withstand without failure is called compressive strength. Compressive strength developed when a material is subjected to compressive load. Tensile strength. The maximum tensile stress a material can withstand without failure is called tensile strength. It is also developed when a material is subjected to tensile load. Fatigue strength. Certain materials are very often subjected to repeated stress. The term fatigue, sometimes known as fatigue strength of a material, is used to indicate its strength in resisting repeated stress. So we can say the maximum stress a material can endure for a given number of stress cycles without breaking is called fatigue strength, or it is also known as endurance strength. Shear strength. The maximum shear stress which a material can withstand without rupture is called shear strength. Yield strength. The magnitude of the stress at which the transition from elastic to plastic occurs is known as yield strength. So we can say the stress at which a material exhibits a specified deviation from proportionality of stress and strain, that is, it indicates the end of elasticity and the beginning of plasticity, is called yield strength. Flexural strength. Strength of a material in bending, that is resistance to fracture, is called flexural strength. Flexural strength, also known as modulus of rupture or bend strength or transverse rupture strength, is a material property defined as the stress in a material just before it yields in a flexural test. Hooke's law. The relationship between stress and strain may be said to be linear for all materials. This sweeping idealization and generalization applicable to all materials is known as Hooke's law. Symbolically, we can write Hooke's law as a sigma equal to E into epsilon, which simply means that stress is directly proportional to strain, where the constant of proportionality is E, and this is the statement of Hooke's law. And this constant E is called elastic modulus, modulus of elasticity or Young modulus. Poisson's ratio. If a direct force acts on a body, it produces direct strain in the direction of its action, and an opposite kind of strain in every direction of action. This is known as lateral strain, while the strain in the direction of action of the force is known as longitudinal strain. The ratio of these two kinds of strain is a constant and is known as Poisson's ratio. So we can write Poisson's ratio is the ratio of lateral strain to the longitudinal strain. It is denoted by mu, and we can write as mu equal to lateral strain divided by longitudinal strain. Hardness. It is the resistance to deformation and forced penetration. In material science, hardness is the characteristics of a solid material expressing its resistance to permanent deformation. In other words, hardness is the resistance to wear. This deformation may be in the form of scratching, mechanical wear, or cutting. Modulus of rigidity or shear modulus. It can be defined as the ratio of the shearing stress to shearing strain. It is denoted by G, and we can write as G equal to shearing stress divided by shearing strain. This is the typical stress-strain curve for mild steel. Stress-strain curve is a behavior of material when it is subjected to load. In this diagram, stresses are plotted along vertical axis, and as a result of these stresses, corresponding strains are plotted along the horizontal axis. In this diagram, we can see various points are marked with this figure, and from this point O to A, the figure is approximately straight, so this is called proportional limit, and this point A is called elastic limit. That means within this point A, the material can return back to its original position after the removing of load. This B is called upper yield point, this C is called lower yield point, and this is the highest point, and this is called ultimate stress point, and this is breaking or rupture point. This is the typical stress-strain curve for concrete. In this figure we can see with the increases of the compressive strength, that is F'C of concrete, the stress also increases. That is the end of our today's lecture. Thank you everyone.